Hello all, welcome to the review packet number 13, video 2. We left off here on number 8, and you're finding limits from infinity. So when you're finding limit and it's approaching infinity or negative infinity, I'm going to show you graphically again what this looks like comparative to what we know. Let's say you have a function and you have a horizontal asymptote like this. When you're finding a limit to infinity, picture your function either going all the way to the right to positive infinity or going all the way to the left to negative infinity. If you were finding the limit of this function right here, both of these pieces are approaching, let's say this is the line y equals 2. You're approaching the y value of 2 all the way to the right and all the way to the left, because as the function is going more and more towards infinity, you're getting closer and closer and closer and closer to this horizontal line. So when you're finding limits to infinity or to negative infinity in every situation, you're thinking about that the graph is going forever in one direction, and what asymptote are you getting really close to? The reason I bring that up here is the logic for 8, 9, and 10 is the same as asking if you're doing top heavy, bottom heavy, or even. So if you looked at number 8, the highest power on the top is squared, the highest power on the bottom is to the 8th power. So this would be bottom heavy, which means that the limit as x is approaching infinity, if you're getting closer and closer to an asymptote, that answer would have to be 0, because when something's bottom heavy, that means it's approaching the asymptote of y equals 0. So the limit would also be 0. I'm going to come back to number 9. Number 10, if you're looking at the limit as x goes to negative infinity, notice that we have 4x squared over 4x squared. So this situation is even, and when it's an even asymptote, that means you have an asymptote y equals, comparing the two lead coefficients. So it'll be y equals 1, which means that the limit as x is going to negative infinity also means that the graph would be approaching but not touching the the horizontal asymptote of 1. So that's why the limit is also 1. Number 9 is a little different only because this is not top heavy, bottom heavy, or even, because we do not have a fraction. Instead, when you're given something like this and you're finding the limit to infinity, it's good to think about end behavior. And when you need to think about end behavior, what I would consider doing is doing a quick sketch of the graph. So this function is an x cubed function with a positive lead coefficient. So it means that this function is going to look like a snake that is rising from left to right. So if you think about end behavior, as this graph goes to the right, the function is going up. As this graph is going to the left, the function is going down. So as x is going to negative infinity towards the left, what is the function doing? Well, it's going down to negative infinity. So the limit would be negative infinity. And that's really what you're doing for 8 and 10, except the reason that these are different is you're approaching an asymptote and not an infinity. Number 11 is asking you to graph the rational function. So the first thing we need to do is ask ourselves if we have a horizontal or a slant asymptote. And the logic is very similar to what we were just doing. So because this function is top heavy, that means I have a slant asymptote and I do not have a horizontal asymptote. To find the slant asymptote, we are not factoring yet. We are going to divide x minus 2 into this function. Now what's nice about number 11 versus other questions we've done is you might notice that we're dividing by something that's linear. And when you're dividing by something that's linear, you could do synthetic division instead of long division. So you could put 2 in the box because you set x minus 2 equal to 0. You could take the lead coefficients of the top, which would be 1, 1, and negative 2. And you can do this division, which is a little faster. Bring down the 1, multiply the 2 and the 1, combine down, multiply the 2 and the 3, combine down. So what this means is because we started with an x squared function, this would be x plus 3 with a remainder of 4 over x minus 2. When you're finding the equation of a line, though, you don't care about the remainder. You just care about this. The equation of your slant asymptote is y equals x plus 3. You could have also done this problem with long division. If you'd prefer, you could have done this, and you still would have gotten the answer of x plus 3. Now, in order to find the domain, this is when we need to factor. So I'm going to come up to the top, and I'm going to factor the top to be x plus 2, x minus 1, and the bottom is x minus 2. So my domain represents everything that I can have, so we need to think about what we can't have. The denominator has x minus 2, so that means that x cannot be positive 2. So my domain is everything else. Negative infinity to 2, union 2 to infinity. This function, what's interesting here is you ask yourself, are there any holes? Well, if you look to see how I factored it up here, nothing cancels out, even though it's tempting to cancel out x plus 2 and x minus 2. So because nothing cancels, there are no holes. But there are still going to be x-intercepts and vertical asymptotes. This is the most reduced version of your polynomial. So your x-intercepts, you're going to look at the numerator. You're going to look at these two pieces. So x plus 2, that means you really have a y-intercept of negative 2, 0, and of 1, 0. And yes, I would like you to write them as coordinates. Your vertical asymptote has to do what's in the denominator still, and so you cannot cross the line x equals positive 2. Your y-intercept, the fastest way to find the y-intercept would be, I would say, plug it into the original function. You know that x equals 0 for a y-intercept. So if you plug 0 into the numerator, you'd end up with just negative 2. And then if you'd ended up 0 in the denominator, you have negative 2 also. So that would be 1. So your y-intercept is 0, 1. And so now let's graph some asymptotes, shall we? We have our slant asymptote that we can graph, and we have our vertical asymptote. So my vertical asymptote is at x equals 2. So that would be here. And then the slant asymptote, y equals x plus 3. You start at the y-intercept of 3, and then the slope is up 1 over 1. I'm just going to make all the dots to make sure this graph looks as accurate as I possibly can get it. So we have our asymptotes graphed. Next thing I want to do is graph the points that we have. We have two x-intercepts and zeros, so that's going to be at negative 2, 0 right here, and 1, 0 right here. We also have a y-intercept of 0, 1, so that's right here. And so I definitely know that this piece of the graph exists, so we're going to go close to the slant asymptote, connect all 3 points, and then close to the vertical asymptote. So there's piece 1. It looks like we don't have enough information for piece 2 because rational expressions generally come with 2 pieces. But I do know from previous examples that we've done that the relationship is diagonal. So if this piece is here, I know that the second piece has to be between the 2 asymptotes up there. And again, what you could do is I know that x equals 6 is definitely going to be in this region. So what you could do is take x equals 6. You could plug that into the original function and make sure that 6, whatever is in that region if you would like to make 100% sure that that region is true. Now that we have the graph, let's answer the limit questions. So find the limit as x is approaching infinity. Well, as my graph is going forever to the right, what is the end behavior doing? So as I'm looking to the right, this piece of the graph is cut off at this vertical asymptote. So I need to look at this piece. Well, what is this piece doing? Where is it going? This piece is going farther and farther up. So your limit would be to infinity. Technically, I could also accept d/e because, again, technically infinity is not a y value you can touch. So I will again write /d/e, but again, infinity is okay. The limit as x is approaching 2, we need to consider the left and the right. So if we're looking at 2, we're looking at the vertical asymptote. If we're looking from the left, the graph is going towards negative infinity. If we look from the right and approaching 2, it's going to positive infinity. So because the left and the right limits are not the same, this one is definitely does not exist. Number 12, another rational function. So I notice right away if I'm asking myself, do I have a horizontal or a slant asymptote? This time, between the two, we have even. We have both our x squareds. So that means I do not have a slant asymptote this time, but I do have a horizontal asymptote at y equals 1 because the lead coefficients for both of these are 1. And you compare the lead coefficients if your powers are the same. Your highest powers are the same. Your domain you find by first factoring. So the top ends up being x plus 5, x minus 2, and the bottom is going to be x plus 2, x minus 2. So before I cross anything out, my domain again represents what I can have. And in the denominator, x cannot be -2 or +2. That means that my domain is everything else. -infinity to -2, -2 to 2, 2 to infinity. Does this equation or function have any holes? This time, yes we do, because the x minus 2's cross on top and bottom. So my hole is 2 comma something. And again, to find the something, you take the 2 and plug it into the reduced version of your polynomial, which is x plus 5 over x plus 2. So if you take the 2 and plug it in, we have a y value of 7/4. If we continue with the reduced version here that I'll box in purple, the x-intercepts is what's left in the numerator, which is x plus 5. So -50 is a x-intercept. And the vertical asymptote is what's left in the denominator here, x plus 2. So if I set that equal to 0, I know that my vertical line I cannot cross is x equals -2. The reason we say x equals again is because we are hitting the x-axis at -2 when we are drawing a vertical line. If I would like to find my y-intercept, again, the fastest way is x equals 0. I would plug that into the original function. You plug 0 in the top, we have 0 plus 0 minus 10. Then the bottom, we have 0 minus 4. That reduces to a positive 5/2. So my y-intercept is 0, 5/2. So if I'd like to graph my asymptotes, this time I have a horizontal asymptote and a vertical asymptote. Horizontal is at y equals 1, so I would graph the horizontal one there. And the vertical asymptote's at -2. Again, I would always start with those asymptotes. So we have where the graph is generally centered first. Then I'm going to plot all the points that I have. I have a hole that I can graph, x-intercept, and y-intercept. The hole is at 2, 7/4. So 2, 1.75. So that would be right here-ish. It's not the best, but it'll do. It's hard to draw the perfectly accurate on my computer screen. We have the point -50, and we have the point 0, 2.5. I like this one because I can tell what sides the graph is without guessing. We have these 2 points on in this, I guess, kind of quadrant of the graph. So you're going to go close to the vertical asymptote, through the intercept, going through the hole, going close to the horizontal, and there's my first piece. The second piece has to go through -50, and I also like the fact that I see the relationship that the 2 pieces of the graph are diagonally related again. So there's my picture. Now that I have my picture, I can find my limits. So find the limit as x is approaching -2, and then on that -2 we have a little negative there, which means we're looking at -2 from the left side. So if we're looking at -2 and the graph is coming from the left, that means we're looking this direction, we're coming down here, and it looks like the graph, as you're approaching -2, is approaching -infinity. So -infinity is a perfectly fine answer for the limit, but again, you could also say it does not exist because it's not a y value you can touch. If you'd like to find the limit at 2 exactly, not -2, so if you're looking at +2, so this time you don't have a direction, so you need to consider both left and right. So if you're looking from x equals 2 from the left, you're approaching the y value of, well, what was the y value of that hole? 7/4. So you're approaching the y value of 7/4 from the left, and you're approaching the value of 7/4 from the right. So the limit has to be 7/4. Which again makes sense because a limit represents a y value you're approaching but not touching. Alright guys, so here's where I'm going to end for this video. I will pick up with number 13 on the next video 3. Thank you.